In Year 1, we looked at the bonding of ammonia, NH3. Ammonia consists of a nitrogen atom with 3 single covalent bonds to 3 hydrogen atoms. This leaves a lone pair on the nitrogen that can accept a proton, where a dative covalent bond is formed, resulting in a positively charged ammonium ion. Since the ammonium molecule is accepting a proton, it is acting as a base. With a primary amine, one of the hydrogens of the ammonium molecule has been substituted with a hydrocarbon group. A single carbon amine is known as methylamine, and a 2-carbon chain amine is ethylamine, and so on. A secondary amine is where 2 hydrogens from the ammonia molecule have been substituted with 2 hydrocarbon groups. If the 2 groups are alkyl groups and are 1 and 2 carbons long, then the amine is given the stem derived from the longest chain, in this case ethyl, and the suffix amine. It will have the prefix N-methyl. The N indicates the methyl group is bonded to the nitrogen. We say it is N-substituted. A tertiary amine is where all 3 hydrogens of the ammonia molecule have been substituted. This molecule is called NN-dimethyl ethylamine, and this one N-ethyl N-methyl propylamine. Note how the ethyl and methyl groups are assigned priorities based on the alphabet, with the ethyl coming before the methyl. The longest carbon chain forms the stem part of the name. Like ammonia, amines have a lone pair on the nitrogen, and they too can accept a proton, and, like ammonia, are therefore bases. The resulting positively charged ion is known as an alkyl ammonium ion, in this case, ethyl ammonium ion. Amines react with HCl to produce alkyl ammonium chlorides. They react with nitric acid to produce alkyl ammonium nitrates, and react with sulfuric acid to produce alkyl ammonium sulfates. Do note that 2 amine molecules are required to completely neutralize the dibasic acid H2SO4. Aliphatic amines can be prepared by heating a haloalkane with ammonia. This needs to be done in a closed vessel to avoid loss of the volatile ammonia. Having the halogen attached to the carbon causes a partial positive charge on the carbon, which can be attacked by the lone pair from a nitrogen on the ammonia in the first step of a nucleophilic substitution mechanism. The second step involves another molecule of ammonia. Although a primary amine is formed initially, this primary amine, because of the lone pair on the nitrogen, is itself a nucleophile and can react with the haloalkane to produce a secondary amine. This secondary amine can then react with the haloalkane to produce a tertiary amine. And this tertiary amine can react with the haloalkane to produce what is known as a quaternary ammonium salt. Consequently, when reacting a haloalkane with ammonia, a multitude of products are formed. It is possible to have a degree of control over the products that are formed. For example, if the primary amine is desired, having an excess of ammonia will favour the production of this primary amine. Having an excess of haloalkane will favour the production of the quaternary ammonium salt. Even so, it will still be necessary to purify the product by distillation. Aromatic amines can be made by reducing a nitro-substituted benzene with tin and hydrochloric acid at 100 degrees Celsius. Sodium hydroxide is added at the end of the reaction to neutralize the HCl.